keeping. So let me see, people are entering. Okay.
One other thing, can you see my cursor on this, my little hand thing on the screen?
I can see your cursor, yes.
Okay, good. Thank you.
Okay. Okay. People are still coming in. Yeah, so with the usually this is not how it works. Usually it's automatic because there's a link to which they connect. But now I'll moderate and add people as they connect, and then we should be good. So good morning, good afternoon, everyone. Thanks for connecting. I'll give a couple more minutes, or 1 more minute for people to join. Today we have the great pleasure of having Dr. Robert Ashford and Dr. Alkis with us today. They are the co-founders of Optimization Direct, and they'll be speaking to us about extending optimization with ODH for FICO Xpress. As usual, today we will open it up also for questions and answers. Dr. Ashford has allowed us to ask questions during the presentation. If you'd like to do so, and for us to keep track of it, please use the Q&A feature on the panel. That way we can keep track of the questions when they're asked, and if they're particularly interesting questions, you can upvote them as well. So without further ado, I will let Dr. Robert Ashford take the floor, and looking forward to a great talk.
Thank you, Carlos. Obviously, I hope you can all hear me. Thank you very much for joining this webinar. I hope to keep you vaguely entertained for the next hour. And if you find that I'm going too fast or going too slow, just comment to Carlos and I'll adjust the presentation accordingly. It's always a bit of a challenge to give these webinars when you can't see the audience or get any feedback from them. So sorry about that. Hopefully the Q&A feature will serve a useful purpose. So we are a small group founded by myself and Alkis Vasikopoulos. And what we do is to help people with very large, difficult optimization models. And we also have a product, which I will discuss during this presentation, called ODH, which is designed to co-work with optimizers, in particular FICO Xpress MIP, in order to deliver some value in the sense of getting better solutions more quickly, enabling you to solve larger models and so forth. So I co-founded Dash Optimization way back now, many years ago, and I'm one of the first co-authors of Xpress MIP. So if you're using Xpress and you've got a bug, maybe you can blame me. Alkis built our optimization business in the USA from about 2000, a little bit before actually, and established a very significant user base there, again helping people with their models and providing the very best in the form of support. Alkis and I founded Optimization Direct in 2014. So just giving an idea of what I intend covering, I'll spend some time looking at ways of solving hard MIPs, and in particular the practical ways you might go about it. Then I'll dive in to our ODH product, telling you basically what it's for, what it looks like, what it does, and hopefully inspiring you to try it. I'll say a little bit about our customers and wind up with an example of my using it for a very difficult problem known as redistricting, which I shall come to obviously later. Now, what I'm about to say really for solving hard MIPs applies to all commercial solvers, be they Xpress MP, Cplex, Garobi, ODH, or whatever. And the topics I'd like to dive into are those of parallelism, determinism versus non-determinism, the variability that one gets in terms of runtime and performance for solving apparently similar models on different occasions, different data, and some methods that you might want to use to get a grip on these difficult hard models, and some tricks that can go with them. So, parallelism, determinism. Well, most computers these days have many cores, and you can get the best performance out of them from using many threads on said cores. You can't usually divide the work that you need to do up into completely independent tasks. The tasks that you're running need to communicate with each other, and they compete for resources. Obviously, they compete for the raw computing power of a core, but they also compete quite heavily for things like memory bus capacity. Now, unfortunately, with optimization, our tasks are usually inherently sequential. So the kind of division of work between the individual tasks is limited by this. So it's a tough nut to crack, really, to parallelize optimization processes. Now, it's kind of handy to get the same result if you're solving the same problem twice, so-called deterministic behavior. Now, to get that deterministic behavior, the various threads that you're running, the various tasks that you're running, need to be synchronized. And this synchronization costs time. There are various ways of going about it. The two most common ones are to have sync points, or indeed possibly just putting information into an information pool and being careful about when that information is pulled out. The cost of doing this depends on the model you have, the hardware you're using, the quality of the program that you're running, and obviously on the number of threads. Now, to give you some idea of the overheads of deterministic behavior, let's look at what happens if you're, say, using 8 threads on a 4-core hyper-threaded or symmetric multi-threaded workstation. Typically, they look about 20%. If you want to use more threads, then the cost rises. Now, I did some experiments with 25 of my users' models using a 2-hour time limit and using our ODH optimizer. As you can see, the synchronization overheads rise as the number of threads rises, much as you might expect. Probably as you might not expect, there's quite a variability between the models that I used and the synchronization overhead involved in solving them. So the spread, if you like, of synchronization costs also rises as the number of threads rises. Again, I guess this is something that you possibly expect. Now, if you're going to synchronize tasks, then you need some measure of work that you've done, some deterministic clock time measure. CPU time, as delivered by most processors, is not deterministic. So you've got to use something else. Some people suggest that you can count the number of retired instructions. You kind of need to go privileged to do that. Most of us use some kind of counter that's embedded in the code itself. And that raises some problems. There is certainly variability in the actual work that gets done for a given rise in the counter. And this variability depends on things like model size, what the algorithm is actually doing, and how the computer has decided to allocate resources to your various threads. And that work variability can be significant. A typical work measure might vary, anything from up to 60%, is rarely less than 7. And this gives us some issues. So if you wanted to use lots of threads, let's suppose you've got a very large parallel machine, 64 cores, something like that, how much power do you get out of the next thread? Well, it depends on how much variability there is in the synchronization time. So, sorry, the work measure and consequently the synchronization time. So, if you can see my little counter hit my little hand here, typically you might be in the sort of 30 to 40% range. So that means that you're on these graphs here, where we've graphed the kind of experienced processor power with the number of processors allocated. If your synchronization overhead is small, you might conceivably get 50 units of processor power out of using the 60 processors. Okay. Realistically, though, you're going to be looking at something like 25 tops. Now, this is entirely a theoretical result, which ignores other problems like bus contention, and they can make the situation even harder to use multiple cores effectively. So what are the pros and cons of deterministic behavior? Well, obviously, if it's deterministic, it's repeatable, and that repeatability is kind of good emotionally. You like to get the same answer when you solve the same problem twice. You like it to take the same path. It makes it easier to analyze your model and to actually test it and give some measure of quality assurance. And if you're trying to set up a model for an end user, it makes it easier to tune the solver's parameters. Disadvantage, of course, are these overheads which slow everything down, potentially wasting computer resources and forcing the user to wait longer for whatever he wants, some solution quality to be hit, for example, say a gap, or some target objective value to be reached. Our users, mostly from the operations research fraternity, and they do prefer determinism. However, performance users of multiprocessor systems might well prefer non-determinism. So, for example, the Met Office here in the UK spend most of their time solving Navier-Stokes equations in sheds full of Cray computers. Typically, they'll have a whole warehouse full of these Crays, and they say, well, determinism's for wimps. We can QA our code and our models effectively without deterministic behavior. They're kind of exceptional, and the computing power required by these MET models is just sort of pushing the envelope of what can currently be done. Now, in the future, we may well move towards using non-deterministic methods, because there's absolutely no way out of the synchronization overhead, and whilst the number of cores that's cheaply available is increasing, the speed of those cores is not improving very much. It's improving a bit. So typically we can get maybe 4 or 5 gigahertz workstations relatively inexpensively now, but 10 years ago we could have inexpensively used, say, 3 gigahertz machines. So it's not a huge increase. Now, as bus design and therefore memory speeds improve, this is going to be more of an issue. Now, many people observe that similar models can take very different times to solve, even if they're the same size. And indeed, the small changes to the data can make large differences to run times. Now, one of the advantages of ODH, which I'll discuss later on, is that it blends various technologies, and this tends to make run times less variable. Using ordinary optimization technology, you can achieve a similar effect by using different methods, sometimes in parallel. So one could, for example, try breadth first branching technique and some kind of depth first or default branching technique simultaneously. Some researchers have achieved a speed up of around a factor of 2 by doing this on some models. You could try, for example, using a heavy dose of heuristics and a much lighter one. Just see what works best. Those reduce the variability, but model size is still an issue. And by model size, I'm referring to things like matrix elements, and in particular, those non-continuous or integer entities, be they ordinary integer variables, binaries, semi-continuous set members, or what have you. It seems to me that quite often these large models contain lots of decision paths and options, and one can often dramatically prune these on particular data instances. And that pruning is better done by the modeler rather than the optimizer itself. Modelers can do a much better job than the standard pre-processing or pre-solved technologies that currently exist in optimizer. Users might also like to consider the granularity that they've captured in their model and the kind of things like time horizons. Is it really necessary to have short time periods right out 6 months into the future, for example? Could you not get just as good an answer if you had short time periods in the immediate future and long time periods later on? This sort of thing can make a big difference to the experience of running optimizers and getting solutions fast, and is often ignored. Another helpful trick in dealing with very large models is using some kind of advanced start, some kind of feasible solution, not an optimal one necessarily, is very helpful in things like pruning the branch and bound tree and seeding heuristics, especially the RINS heuristics. Now, one can often calculate such a feasible solution cheaply in advance by solving a smaller model, one that has, for example, much larger granularity or fewer options, or perhaps you've got some kind of model specific heuristic that you can run up front. And it's very helpful to do this before attempting to solve on the full model. Another aspect which is sometimes forgotten is knowing when to stop. By default, optimizers stop when they've reached a very small optimality gap, typically about 0.01%. Now, this is not terribly helpful if your data is only accurate, say, to 1%. It might be sensible to strive for a 1% solution. So think about the quality of your data and really how small a gap between the current solution and the best bound on it that you actually require. Obviously, if you're using application system or you're down there in the weeds using the API of a solver, you can use more sophisticated criteria, such as reaching some kind of target objective, some kind of pre-computed lower bound, and so forth. Most optimizers, and Xpress MIP is no exception, have a thing called a cutoff, some kind of objective value above which, or where your objective is less than, which defines whether a solution would be useful. So if you're minimizing and you're really looking for an answer that's, say, less than 1 million, then you're not interested in solutions with an objective value of, say, 2 million. And specifying this in advance is sometimes helpful for speeding up the optimizer. Now, I'd like to spend a few minutes now discussing our ODH product, which is a set of tools for handling large or difficult mixed integer programs. It co-runs with a major solver. I'm going to talk about its co-running with FICO Xpress MIP optimizer. It's designed to exploit parallel hardware, and it uses the solver, in this case Xpress MIP, internally. It's designed to be good at getting solutions, and in general is more powerful than just using the optimizer, in this case Xpress, on its own. So the idea is that it extends the footprint of the optimization methods themselves. Models are becoming larger and more complex. Users are always pushing the envelope of what they can do, and standard optimization technology sometimes gets pretty stretched. Now, most people appreciate that as size and complexity increase, so does solve time. And most people also appreciate that this increase is faster than linear. The reality, unfortunately, can be quite a lot worse than this. And to illustrate this point, I've solved a large number of models of different size, really in the same structure, taken from submodels of a scheduling model, and it is kind of interesting. So if we graph the number of integer entities, mostly binaries, but with some integers in the scheduling model, against the time to reach the default gap, 0.01%, we see that for many of them, the small ones, the time is really quite short. But then you hit a point where the time starts shooting up. And up here at 2 hours was where I set the time limit. And it's almost as though you're hitting a performance barrier here. Now, having said that, as I mentioned before when talking about variability, there are some models which are small but still take a long time. The trend, though, is for there to be some kind of fairly tough barrier, at which point solution time increases dramatically. Now, our ODH technology has a number of algorithms in it, and I think it'd be helpful just to say a few words about them. The idea is that we start off by trying to find some kind of initial integer solution. Might not be feasible, but some kind of initial solution that we can work with using a local search method. And then we set about improving it. If the solution is currently infeasible, we try and find a solution which is less infeasible in the standard phase 1 may. So we do this by decomposing the original model into lots of submodels and finding better solution to the submodels, not necessarily optimal ones, and then combining the solution from the submodels to a solution to create a solution to the original model, and then repeating the process as we change the decomposition. The idea is that each submodel solve sits in its own thread or set of threads, and we use the parallel hardware as much as we can. So we repeat this with fresh decompositions. The decompositions themselves are derived by a variety of means. We can use some kind of RINS base or even a local improvement based heuristic to do the decomposition, but mostly the decomposition is done by looking at the matrix structure. this structure can be specified by the user, or it can be automatically deduced by the system. Sometimes the user can specify a structure more completely than can be inferred automatically, and it's helpful to use it. But quite often, the automatic decomposition works perfectly well. In fact, given that we work on a pre-solved model whose structure is often quite different from the original one that the user wrote, this automatic decomposition can often be quite a lot better. So how does it work? Well, we run the main solver, in this case Express, and ODH in parallel, and they exchange information. So Express will tell ODH about the models that it's solving, solutions it's found already, any bounds that it's tightened up, and any relaxations that it's solved during the root process, and subsequently, perhaps after a restart, it might impose cuts, and it can tell ODH about those. ODH grinds away and injects solutions into the main Xpress MIP solver. What does it look like? Well, it looks like any other commercial optimizer MIP solver. It could be run from the command line with a simple command line tool, and it's got library interfaces for connecting with programs in C or C++, Python, and Java. It uses Xpress MP's API and its own specific calls to do things like manage parameters and callbacks, initiate optimization, terminate the optimization process, and so forth. ODH is available in various applications such as GAMS, MATLAB, and AIMS, and ODH Express as a variant or a new version is in progress, being implemented within these applications. I hope that we will have it in AMPL at some point soon. I know that one of the AMPL developers has registered for this talk, and just a hint there, let's get on with it. Currently, ODH runs on Windows and Linux. I have heard recently that the ARM solvers used, say, in Macs are very, very effective for optimization tasks. So we may be looking at a Mac implementation very soon. Now, does this stuff actually work? Well, sometimes it works better than others, obviously, like most optimization technologies. And it works best on models that are kind of too large for your main solver to deal with quickly, and have many integer solutions, preferably integer feasible solutions, and that you can hop between. And it is good at actually finding these feasible solutions. It's good at finding an initial feasible solution, and it puts a lot of effort into that, which can be helpful for models where the main solver, in this instance Express, finds it very difficult to generate a feasible solution. And it's very useful when you want a good solution rather than something that's proven optimal to, say, 0.01%. Now, I claim that the technique really does work. We've collected, well, it's now pushing almost 1,000 customer models, and from that, I have selected 100 to use as a kind of benchmarking subset, and I test ODH on this regularly, typically with 8 threads on 4-core Intel workstations using a 2-hour time limit. And on the 100 models that I've actually selected quite randomly, it does reasonably well. So of those 100 models, Express manages to solve 25. ODH with Express inside does the same. but it gets feasible solutions to 90 out of the 100, as opposed to Xpress's 83. I should add that a couple of those models are actually infeasible and are put in there for testing purposes, so the performance is a little better perhaps than might first appear. Now, at the end of the 2-hour time limit, I take note of the gap that's been achieved, and ODH manages usually to get a smaller gap. On average, using some kind of arithmetic mean, we get a gap of about 16%, as opposed to the solver on its own, which gets a gap of over 24%. This is where I would take a run in which no solution was found to have a gap of, say, 100%. It's a bit arbitrary, but it gives you a reasonable measure. Looked at from the perspective of a shifted geometric mean, the gap reduction is slightly better, giving us a 37% average geometric reduction. So 37% reduction in the geometric mean, the final gap. So on these models supplied by our customers, so it's a bit self-selecting, I guess, ODH works pretty well. Now, when we first developed this technology, the group at ZIB, who managed MIP, produced a new set of models, the so-called MIP 2017 set, and we ran ODH on some of them a couple of years later. Now, of those models, 286 were declared to be open in the sense that no optimal solution had been proven to them. And in fact, no solution at all had been found to 29 of those models. And we tried ODH on this set using entirely default settings, just running it for a couple of hours. And what did it do? Well, it managed to prove optimality on 13 of the models. This is with the 8 threads running on a 4-core workstation. It did a little bit better using an Intel Xeon server, where we were using 16 threads on a 24-core machine. So we were getting some kind of optimality proof there on models which were previously open, and it found better solutions to those that were regarded or recorded as being best known to a very significant portion of those models. In the case of using 4-core workstations, we got better solutions to 39% of them, and using the 24-core server and 16 threads, we got better solutions to 45% of them, almost half. And as a kind of bonus, we found feasible solutions to 5 models where no solution was previously known. Now, that was not long after that model set was published. Since then, of course, lots of people have worked hard on trying to solve these models. And indeed, if you go to the MIP website, you will see that researchers have managed to beat Xpress on quite a number of them. But I thought it useful to give you an idea of how ODH performed using simple default settings and a very limited time limit, 2 hours, before people have started diving into individual models in detail. We have customers, and they're drawn from quite a variety of industries. Quite a number of them in retail. Energy is a big one. Process industries, pharmaceuticals, telecoms, fairly significant, and we even have customers from the health sector. What do these people want to do? Well, they might be wanting to solve supply chain models. Got a number of customers doing that. Network design tends to be a difficult thing, particularly in the telecom sector, and ODH is pretty handy for addressing these models. Our first big customer was interested in scheduling satellites, and he still uses ODH. In fact, ODH is indispensable to his scheduling models. We've also used ODH effectively in workforce scheduling, distribution models, and in sales and operation planning. Our customers want mainly to find good solutions quickly. By good solutions, solutions that we can prove are to within 2 or 5% of optimality. Sometimes they want optimal solutions and you want to get there faster. And some of these users, ODH is effective at doing that. Obviously, the more quickly they can get useful information from their model, the more they can explore its structure and understand what's going on. These models tend to be very large and quite often quite complicated as well. Now, just to give you an idea of its performance as time goes by on customer models, I've looked at a small set of the ones in our test set and graphed the best bound and the optimal solution against time. The ones that I've selected are all quite large and they're all pretty hard. We're running on these modest Intel workstations with only 32 gigabytes of memory. So a couple of them do tend to spend quite a lot of time paging, frankly. All done with default settings and a 2-hour time limit. Here is a planning model where I've graphed the solution found by Express in a solid red line and the best bound found by Express in a kind of dotted red line. And as time goes on, as you can see, the Express solution gets better. We're minimizing so it gets smaller and the best bound rises, which is what you'd expect. Now I've done the same for ODH Express, where I've used green this time, a solid green line for the solution that ODH has found, and a dashed green line for the best bound found by ODH. This is typical, I guess, of ODH's behavior. So by and large, we get good solutions more quickly, but there's effort involved in getting those solutions. To run ODH, we need to take away threads that could otherwise have been used to run Express. So what you expect, of course, is that since ODH doesn't really do anything to raise the best bound, we would expect Express on its own to raise that best bound more quickly, and this is indeed what happens. Okay. As time goes on, you might hope that ODH would get a best bound that's almost as good as Express's, and that happens in the majority of instances. Although you can see here, there's still a little bit of a gap between the best bounds provided by the two technologies. Right, here's another model, this time taken from a customer who does network design, particularly for fiber optic networks. Again, you can see that ODH manages to get better solutions more quickly, and this time the best bounds given by the two optimizers are pretty much identical. Right, here's another fiber optic model. Again, quite a beefy model with over 1 million integer entities in it and 6.5 million non-zeros in its matrix. Express does sort of okay in the end. It finally gets a reasonable solution after an hour and a half, and it doesn't manage to move the best bound much. ODH, on the other hand, manages to get better solutions much more quickly. So if we wanted to terminate with a reasonable solution, we might be able to do so after an hour or so, whereas with the Express on its own, that wouldn't be practical. In this instance, the initial solution, feasible solution, was found by Express. So you can see here they both start at the same point. Right, ODH doesn't always work. So here's another network, fiber optic network design model. Different structure, rather smaller, but possibly somewhat harder. And although the ODH does deliver some benefits, they're relatively modest by comparison to, say, Express on its own. Now, here's a model taken from our first big customer who are scheduling satellites. This is a model that optimizers were unable to find a feasible solution to. I don't think any of the commercial optimizers can find a feasible solution to it with default settings. ODH, on the other hand, manages to get through its phase one and get a feasible solution after 20 minutes, 30 minutes or so, and then manages to improve it as time goes by, and it keeps on improving it. If I let the program run more than 2 hours, we will get a significant reduction in the gap there. The gap from both Express and ODH is bounded as by the best bound here, and that is pretty much the same for both optimizers. This is not a huge model, but pretty tough. I mean, in the early days of solving this guy's models, Cplex couldn't even get through the LP root solve in 2 hours. Whereas both Cplex and everything else has improved since then. Express does manage to get through that quite smartly, but even so, actually processing that root LP solution by adding cuts and so on takes an awfully long time. And by the end of the 2 hours, I think we've done about 1 round of cuts with Express. So it's tough numerically. This goes to show the benefits of reducing model size exploited by ODH in this instance by working on sub-models, much smaller versions, if you like, just taking a few entities out of the big model and dealing with those separately. Now here's a supply chain model, again one which is quite numerically challenging, mainly because of poor scaling, and it's one where Express does reasonably well, actually. But ODH, there the ODH solution being the green line, manages to drop much more quickly, and we're getting pretty good solutions here after half an hour. So in that application, ODH is very handy indeed. Now here's an interesting model. This one's got lots and lots of special ordered sets in it. Again, quite hard to find an initial feasible solution. In this instance, Express found a feasible solution first, and ODH used it. And you can see that ODH managed to get a much improved solution very quickly. You might think, well, it's not moving much after that, and if you're prepared to wait an hour and a half, then it's just as Express will be just as good. I mean, I mean no offense to Express in this matter. This is the same kind of behavior that we would observe with any optimizer with default settings. However, It's kind of interesting here because if you look at the lower objective function values in more detail, you get something like this. So you can see that a meaningful usable solutions are only ones where you've got a negative objective. We're minimizing was actually really a maximization model, and have switched the objective signs to the objective function coefficients. So up here we're losing money, down here we're making it. In this instance, ODH managed to get usable solutions at the end, whereas the ones from the standard optimizer were not usable. Right, here's another model from an unknown source. It came to us from an application vendor. No special order sets, just binaries and integers, but relatively beefy with 13 million non-zeros in its matrix. Again, ODH manages to get reasonable solutions much more quickly. So after an hour or so, it's got something that the user could use. Here's another one with a similar story, although in this case, ODH managed to get very close to its final solution after half an hour. Yes, I must apologize for the somewhat kinky graphs here. This is an artifact Excel, I'm afraid. So you get the idea. So I claim that ODH is necessary for applications in areas as diverse as satellite management, forestry, retail, fiber optic network design, and so forth. I have myself used it for redistricting. Those of you in the US will be aware that every 10 years, the government does a census of the whole country. After that census, electoral districts have to be redrawn, usually so as to balance population. So each district has got to be equisized, or as close as you can get. And this redrawing exercise can be somewhat controversial. One might try and use a scientific approach using MIP optimization, but the models one gets tend to be pretty big. A kind of medium-sized one that we've looked at has around 35 million columns in it, of which 5 million would be binary. So just no integers, just binaries. And the matrix is pretty beefy at 130 million elements. We have used our technology on models that go 5 times bigger than this. Usually you can scratch around and get a starting solution, but they might not be very good. What we're aiming for is a 5% gap where we're trying to balance various things. We want the districts that we're drawing to have equal population size or near equal population size, and we want to make sure they're contiguous, of course. You can't have sort of isolated pockets. You want to achieve a number of other objectives, such as having a majority minority if you possibly can. So if you've got a minority in your state and it's possible to draw a congressional district with a majority of minorities in that, then you are legally obliged to do so. And we managed to get reasonably good districtings using runs typically up to 8 hours on a 24-core Xeon server. Here is an example of drawing the congressional districts for the state of Virginia, where we had the maximum population deviation. That's looking at the difference between the largest district and the smallest one in population size of less than 1.5%. And that's normally considered okay. although administrators could object and demand absolutely equal populations. It's a trade-off. Usually one can get them to accept something like this. In this particular run, we managed to get one district which has what they call a minority majority in it, i.e. majority of minorities. That happened to be district number 4, which is that one. It's a good idea, as well as keeping these districts to be nicely shaped, to avoid splitting up things which are, kind of meaningfully placed together. So counties, for example, shouldn't really be split if you can avoid it. And we only needed to split up 4 of those counties. You can see all the counties there identified on the map. I don't know whether you can quite make these out. That's a big one, for example. There are smaller ones up here. So that worked, and went to the legislators for consideration. The legislators, of course, have got their own agenda, going back to the days of Elbridge Gerry in Boston in 1812. The party managed to draw districting in which one of the districts looked like a salamander, hence the term gerrymander. So it's been political from the outset, hundreds of years. But if we can get people to try and address these problems scientifically, that puts a kind of democracy issue behind us. In conclusion, then, I would claim that customers want to solve larger and larger models. There are hard barriers to solving them, particularly to optimality, or even getting a solution at all. ODH can find good solutions, and it's sometimes useful on smaller and easier models in getting proven optimality more quickly. Right now, I think parallel solution methods are the best way of exploiting modern hardware, although things like GPUs are coming into the frame, and being useful for some very large applications, typically with primal dual methods. There's a long way to go before those technologies are able to deal effectively with MIPs. So if you want to solve a MIP, I would claim that parallel solution methods are best. And what we're trying to do is to exploit modern hardware as much as we can. Currently, the main limitation in our doing that is that of memory bus speeds, but they are improving, and we have been promised improvements for quite some time now by the likes of NVIDIA. Thank you for listening. There's a few minutes for questions left, if anyone would like to ask them.
Well, thank you, Dr. Ashford. I'll open the floor with questions by asking a question myself. So it seems that ODH also has its own APIs. What languages are they in?
Well, the base libraries use C, just like Express does. But you can access them via surrounding layers in Python and Java at the moment.
Okay.
I mean, I've even got models running with BCL. Everyone throws up their hands in horror at the idea of using BCL these days, yes. But it does work.
Yeah. Okay. Okay.
And my preference is for Python, and you can specify decompositions really quite neatly using Python.
Okay. And for example, is it possible to? You said there's a command line interface as well, right? And so
yes,
is it essentially reading an MPS file and then it will run ODH on top of it without having to do any specifications, or are there additional things that need to be configured through the command line interface?
No, you can just run it on an MPS file, an LP file, just the same as you would the Express Optimizer itself. You can even, if you want to, run it inside the FICO Optimizer.exe command line tool.
Okay. Okay. And what about interfaces, open source interfaces like PyOpt interface, Pyomo, and so on? Is there an integration or an interface to play with it directly?
Pyomo has an interface mechanism which is entirely file-based and could drive ODH without any problem. Obviously, most Pyomo users want to see a tighter interface, which you've got with Express, for example, and I think Pyomo have got it with the other major solvers. We haven't done that yet.
Okay.
We will respond to demand if people want to do this. I'd like to encourage people to use the Express Python interface because I think it's really nice. You know,
Yeah.
I've got a lot of experience using the Cplex one, some experience using the Groby one. I think the Express one is the more intuitive.
Yeah. Yeah. Same. Last thing, well, from my side, I don't know if there are any other questions from other people. In the benchmarks that you showed, I might have missed it, but were you comparing default configurations for
Yes.
Express? Okay. Okay. So they weren't fine-tuned.
The defaults in all cases.
Okay.
I mean, there's some argument for saying, well, if you've got a hard model and you want good solutions, you should compare it against Express running in kind of heuristic heavy mode. And I've not had the opportunity to do that yet.
But also the defaults are for both, right? ODH defaults and
Yes.
Express defaults. So you're not doing any specific decomposition, being like giving ODH specific decomposition.
No, it's all the decompositions are done automatically.
Gotcha. Okay, perfect. Thank you. Are there any other questions from people on the line? You can feel free to use the Q&A or raise your hand and I can allow your microphone. Okay, if not, I want to thank Dr. Ashford for your time and appreciate you sharing your studies and providing this perspective, right, of leveraging modern hardware architecture to speed up solving these difficult mixed integer programs. Thanks everyone for your time and appreciate it. And be on the lookout for the next Express talk, which will likely be about building cost function approximation using the FICO Xpress stack. So be on the lookout for that. And again, thanks everyone for your time and have a great weekend.
Right. Thank you very much.
Thanks everyone.
Thanks everyone. Cheers now.